Neural nets map input to output with some computations in between. Usually we feed the clean data to our model. But what will we obtain if several precomputed features are also passed to the network with the raw data? In econometrics, this leads to multicollinearity. And multicollinearity invokes higher dispersion of the estimated parameters. But network parameters are another story. However, bias variance trade-off is on the table. Long story short, my question is, do results differ if we add some unlearned mutation of the data? Let's try it. I take weekly initial claims from Fed. They're from late 60s until now. And of course, we will work with the relative weekly changes. I add the 4, 8 and 16 moving averages and corresponding standard deviations. So we have 6 additional parameters. We also take a series of 17 values to predict the next one. In total, 23 values for analysis. For comparison, we use the data without moving averages. The network itself is very simple. Only 5 layers with a hidden size equals number of features times 4. Why not? Of course, for real forecasting task, it's worth trying convolutional layers with transformer and etc, but now I don't care. Now I want to know the consequences of potentially processed information. In fact, we use some sort of pre-calculated convolution. We just do not train it. This is the result we got from the precomputed data. And if we don't calculate in advance, we get this. It turns out that the additional precomputed data improves our model twice, and that's great. Of course, my goal was not to create a maximum plausible model to predict weekly initial claims. I wanted to see the difference in the preliminary preparation of data that is already contained in the pure form. It seems that such help to the neural network does have a certain effect. And what the field for researchers arises, doesn't it? On the one hand it's good, but on the other it's a bit strange, don't you think?